Okay, so now I'm going to say to myself, I'm going to apply this a somewhat different way. Okay, and I'm going to take a look at this. The mean SAT score for the population of first-year students at Hunter is 620. That's the mean for all first-year students. The standard deviation of scores in this population is known to be 95. So I know their mean and I know their standard deviation. An investigator believes the mean SAT score for first-year psych majors is different than the mean of psych scores for the entire population. It's different than the entire population. The mean of this, he takes a sample of 36 first-year psych students and finds that the mean of their SAT scores is 648. Okay, so let me see. Let's write down what we know here. Okay. So what do we know here? We know that for all students, right, the mean mu, right, because we know what it is for all students, is 620, and sigma is 95. Okay, and let's see. But now we're interested in how this compares to psych students. Well, psych students, we didn't have the time to sample all the psych students. So we were only able to get a sample of 36. And the mean there was 648. X bar is equal to 648, right? And the sample size was 36. I'm going to say to myself, you know, I have no reason to believe that the standard deviation for the psych students is any different than it is for all students. So I'm going to use the same standard deviation, maybe a little bit of a reach, but I'm going to use the same standard deviation and say I know the standard deviation of this population. So now I want to see if I can apply this to say whether or not there is a difference between these two populations. Okay, so the way I'm going to do this is first, I'm going to set up a couple of hypotheses, right? I'm going to set up a null hypothesis, and I'm going to set up an alternative hypothesis. Okay, so my null hypothesis is, what do you think our null hypothesis is about the means of the total population and the mean of the psych majors? They're the same. Okay, I'll write that this way. Remember, I'm talking about the mean of the population. Mu of all equals mu psych. Right? What's the alternative? What's the alternative to that? It should be an A there. Mu of all does not equal mu of the psych students. Okay, so now let's set about testing that. And one of the ways I might be able to test this is to see how far apart these two values are in terms of standard deviations. Right? Remember, where a 95% confidence interval was based on this idea that if we were within two standard deviations either way, that we would catch 95% of the possible outcomes. So I'm going to put that to work right now, and I'm going to say to myself that the z value, the difference for these two, I'm using z because I'm saying I think I know the population standard deviation. The number of standard deviations between these two groups is going to be, what's it going to be equal to? Let's see. It's going to be equal to the difference between X bar and the mean of all. X bar for the psych students, which is all I know, and the mean that I know for the population. This is a known value, right? This is just a sample value, right? This is what we call a single sample t-test. I've simplified it here by saying that we know the population standard deviation, so we can use the z-score, right? But we normally call this a one sample t-test. Why is it? Because I'm only taking one sample and I'm comparing it to a known value for mean, right? Or something that I speculate I know well enough to call my known value, right? So it's the difference between the mean for my sample versus the mean for all students divided by, what do you think I'll divide it by if I'm interested in the number of standard deviations? I'm going to divide it by the standard deviation, sigma, right? Just like we did before with our various populations and so on. Okay, so now, I'm sorry, excuse me. Yeah, good work. It's standard error, right? Why is it standard error? Because we can't forget that the sample size is going to have an impact on this. We're comparing our mean of our sample to all the possible means we could have got instead. So really, we don't want to use the standard deviation. We want to use the standard error. And what's the standard error going to be equal to? It's going to be equal to sigma over the square root of the sample size, which was 36, right? So what is that equal to? It's equal to 95 over 6. And what's that? Oops, I lost it. I don't know what happened to my, I lost my, what's that? 15.83. I'm going to call it 15.8 for our purposes for now. So that's equal to 15.8. So what's our z-score equal to? It's equal to x bar, which is 648, minus, what does it mean for the population? 620, right? Over 15.8. And since I lost my calculator, I'm dependent on you guys to tell me what that is. What was that? 1.77. That's our z-score. So what are we saying here? We're saying that these two values, that if I were to draw this distribution of all the samples that I might get, for given that my mean is 648, my sample size is 36, I'm assuming our standard deviation is 95, then how often would I expect to get a value as far away as 620? Well, it's only 1.77 standard deviations away. So is that more the tail end there? In other words, the values, the percentage of the time I would expect to get a value that small, is it less than 2.5%? What I would expect if I wanted 95% certainty or 5% chance of being wrong? Well, no, it's not. It's not greater than 1.96. If it's not greater than 1.96, it's not far enough away from the known mean, or the two values are not far enough apart from each other to be able to say that I have only a 5% chance or less of that being the actual same value for the two populations, that occurring if I took samples of that size from the real population, right? So do we get the idea here? What I'm, I'm perhaps not as explaining this as clearly as I would want to. I'll think about it. I'll think about another way to do it, maybe for one of the homework examples or something like that when I do a review. But in order for me to say that I'm 95% sure, less than 5% chance that I would be wrong, and if I said this, in order to be able to say that, the two values would have to be two standard deviations apart, or greater than 1.96 standard deviations apart. Okay? So since it's only 1.77 standard deviations apart, can I go back here and say with 95% certainty that, I don't remember where I put it. Oops, where did I write that? Did I write that on here? Here, it's my null hypothesis. Can I say with 95% certainty that I can reject the idea that they might be from the same population, right? I can't, because I need for the z-score to be bigger than 1.96. So what do I say now? I can't say I reject the null hypothesis and accept the alternative hypothesis. What can I say about this now? Anybody want to hazard a guess? Can I say that, oh, I've just proven that the mean for psych majors is equal to the mean for everybody? Have I proven that? No, I haven't. What I really wanted to do was be able to reject this and accept the fact that they're different, with a small chance of being wrong, right? So I can't say that this is true. All I can say is I fail to reject the null hypothesis. In order for me to reject the null hypothesis, I have to have less than 5% chance of being wrong. And in order to have that small a chance of being wrong, these two values have to be 1.96 or more standard deviations apart. Okay. Now let me ask you something. If this sample size had been 16 instead of 36, how many standard deviations apart do you think they would have to be then? Would it be 1.96 again? It'd be the t-score. What was the t-score? We just did it for 1.96. 2.13. They'd have to be 2.13 standard deviations apart for us to be 95% sure that they're different. In other words, less than 5% chance of being wrong if we reject the null hypothesis. Okay, that's how now we're starting to shift away from this idea of confidence interval and start to apply the same ideas to the idea of comparing two groups. In this case, we're not really comparing two groups yet, right? We're comparing a sample result to a known value, one sample.